Hi, and welcome to the Unit 5 test review. So our goals for this unit were to explain how chemical reactants combine to form products, interpret and label a reaction energy diagram, identify factors that influence the rate of chemical reactions, and describe reversible reactions and equilibrium, and finally use Le Chatelier's principle to predict the predominant direction in which a reaction will proceed under defined conditions. So we'll get started. The first thing that we covered was the idea that chemical reactions proceed sort of like the fairy tale The Princess and the Frog. We talked about collision theory with this. So just the idea that for a chemical reaction to take place, you need two reactants and there needs to be a collision between them. When we're relating this back to The Princess and the Frog, it's sort of like the kiss. So as soon as reactant 1 and reactant 2 collide with each other, that temporary collision of reactants in just the proper orientation prompts the formation of one or more new chemical products, just like it transforms the frog into a prince. We also discussed how molecules are in constant motion and they have varying speeds and adopt various orientations. And in order for a reaction to actually take place, the reactants need to align with the correct orientation, and they have to collide with the correct amount of energy. And some reactions take more energy than other reactions. Now, when these particles actually collide with each other, they form what's called the transition state. So the transition state is what you see here in the middle. It's something in between the reactants and the products. It might also be referred to as an activated complex. And this is the highest energy form in the reaction. So the energy that we actually need to turn our reactants into this transition state is referred to as activation energy, and it's abbreviated as E sub A. Some reactions require a lot of energy to do this, and some require a little bit of energy. And then to go from the transition state to your final product, sometimes you'll have to put energy into the system to get this to happen, and sometimes you'll release energy out. So this graph right here actually shows energy being required. So here's the energy of the reactants down here. This is a rather large activation energy to get it to the transition state. And then here's the energy of the products. So the energy of the products is higher than the energy of the reactants. This reaction requires energy to be put in. Now, this reaction is different. This is going to release energy into the environment. Because you start with higher energy reactants, you have to put a little bit of energy in to reach that activation energy to turn the reactants into the transition state. And then when you go to the products, you actually go down in energy, and that's going to release energy out into the surroundings. So looking at this right here, we want to match the portions of the energy diagram to the reaction species that they represent. So letter A is right here. Letter A represents the reactants. So letter A represents the reactants. Letter B represents the transition state. So letter B represents the transition state. Letter C represents the products. So C is the products. And D is the activation energy. So this is the activation energy, the energy required to get the reactants to turn into the transition state. And then this specific reaction right here releases energy, because the energy of the products is less than the energy of the reactants. This transition state that we form, so here's the answer to the previous question, A, reactants, B, transition state, C, products, D, activation energy. This transition state is very temporary. It's a very temporary thing. It'll sometimes only last like maybe a millisecond, if that. Probably not even that. It's so quick. And you are more likely to get a reaction to form if you have many collisions, because remember, it's the collisions that provide that activation energy that get the reactions going. So if you have more collisions, you're providing more activation energy, you're going to increase your rate of your reaction. So your reaction will be more likely to occur. We also discussed the factors that affect reaction rate, which are temperature, surface area, concentration, and pressure. So remember, with temperature, as we increase temperature, we increase the speed of the molecules, and we also increase the number of collisions that they had. This actually led to a faster rate of the reaction because there were so many more collisions, so the reaction rate got faster. You had more reactants colliding with each other at the correct orientation and with the correct amount of energy. Surface area also affected the rate of the reaction, and remember, for surface area it was a little bit different. So surface area did not affect the movement of the molecules in any way, shape, or form. All it did was provide more opportunity for reactants to collide. So this would be low surface area, here's high surface area, because you have these additional sides right here where the reactant can come in and collide. Concentration was another factor that affected the rate of reaction. So if we increase concentration or amount of reactant per volume, we got more reactions taking place because there were more reactants present to collide with each other and provide the activation energy to get that reaction going. And finally, pressure. So when we increased the pressure, we increased the speed of the molecules, they collided more, and the reaction rate went up. So in terms of increasing reaction rate, concentration, temperature, and pressure all worked by causing more molecule movement. So they caused the molecules to move around faster, collide into each other more, and that's why the rate went up. Whereas surface area didn't really affect the molecular motion at all, and actually it just provided more opportunity for collisions. And then here's the graph for each of these. The important thing here is that if you increase any of these, you increase reaction rate. So they all increase as the other one increases. So increase concentration, temperature, pressure, or surface area, and you will increase rate of reaction. And then we briefly mentioned catalysts and inhibitors. Remember, catalysts lowered the activation energy and increased the rate of the reaction. Inhibitors did just the opposite, so they actually slowed down the reaction rate. And we talked specifically about biological enzymes, which are an example of catalysts. So inhibitors, they were the opposite. They decreased the reaction rate by impeding collisions from occurring. And impede just means stop, so they sort of prevented the collisions from occurring. Then we got into the idea that reactions are reversible, meaning that you can have A plus B going to C plus D, or C plus D could go back to A plus B. So we could actually turn our products back into reactants. And we also talked about the idea of equilibrium. Equilibrium it wasn't necessarily when A plus B was equal to C plus D, because remember, equilibrium does not mean equal. Rather, it was where you had a constant amount or concentration of products and a constant amount of reactants. So this is the graph right here, and over here on the end, this is where you actually see equilibrium right here. So the blue is the concentration of products that increased over time, and then once it got up here, it sort of flatlined. This is equilibrium right here. Reactants, they decrease, 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 and then as soon as they flatline right here, that's when equilibrium has been reached. So as time passes, the amount of both reactants and products level off and become stable. Once they're stable and the concentrations don't change very much, that's equilibrium. It does not mean that the products are equal to the reactants. That's not equilibrium. And actually, most of the time, they're not equal to each other. You could have 1,000,000 products for every one reactant, and it could still be at equilibrium. And finally, we talked about Le Chatelier's principle, and this related to reversible reactions at equilibrium, and basically said that any change to the system will cause the reaction to move in a direction to offset that change. So for example, if you add in more reactants, equilibrium will shift to the right to make more products. So if you're adding more A and B, that means you're increasing the concentration of A and B, so more of A and B is going to be converted to C and D so that you can go back to equilibrium. If you remove some of each reactant, then your equilibrium is going to shift to the left, and you're going to get more reactants being formed. So if you add more of the products, it's going to go to the left. If you add more C and D, you're going to get more A and B. And if you remove some of each product, it'll go to the right. So if you remove some of the products, A and B will turn into more products. So consider the following reaction at equilibrium. If we add reactant A to this reaction. So if we add A to this reaction, it's going to cause more products to be formed, and it's going to shift the equilibrium to the right. So this bottom one right here is correct. If we remove A, then it's going to actually cause fewer products, and it's going to shift our equilibrium to the left. And here are some other reasons for shifting equilibrium. It could be due to changes in concentration of products or reactants. So if we add in more reactants, or if we take away products. Temperature changes can also affect equilibrium, and the same thing with pressure changes can affect equilibrium. So that is it for our test review. There's also a Jeopardy game that you guys can play. I have the link on the whiteboard, and I'll also send it out in a K-mail and link it in the class. So you have that form of review as well. So what you guys should do is make sure to study for the test and do your best. I'm sure you guys will all do great. All right, that's all I have for you.